Welcome everybody to the first colloquium of the year. It's my pleasure to introduce today Maksym Radziwill from Northwestern. Radziwill, okay. From Northwestern. Maksym studied here in McGill for his undergrad, and then he moved to the West Coast to study with Soundarajan. After his PhD, he held several positions here at McGill again, at Recherches, at Austin, at Caltech, and is now back in Northwestern. He has won several prizes for his work in analytic number theory, such as the Sastra Ramanujan Prize, the Sloan Fellowship, the Coxeter James Prize by the CMS, and more recently, the Break II Prize and the Cole Prize of the MS. And it's my pleasure to introduce his talk of today, which is branching processes in random matrix theory and analytic number theory.
Okay, so thank you for the invitation. I wonder if this works. This thing, does it work?
If it doesn't work, we
Okay, not a problem. Okay, so basically the topic of the talk is this intersection of these three subjects, which seem quite disparate. So I'll just I'll start by motivating with a purely physical problem. Okay, so we have this kind of setup. So why do I start with a physical problem? I kind of notice actually physical problems give a lot of intuition about analysis. So if you're able to cast analysis into physics, you get a lot of intuition for free, because you start to be able to use your daily life intuition to actually get a good common sense understanding. So here is the setup that we have. We have about 10 to the 23 particles, or whatever huge number it is. I choose this number because that's about the order of magnitude in a typical material, so why not? And then all of them lie on the unit circle. So we have basically a situation where you have the unit circle, and on this unit circle you have some particles here, all of them negatively charged, right? So they all repel each other, essentially. And the energy between two of them, so let's say if you have one Z1 here, Z2, then the energy that is between them, the potential energy, is just the log of 1 over their distance. Which makes sense, because if they're very close together, they repel each other very much. If they're far apart, it's much less, okay? And so then if you have many of them, here, then if you sum over all the 2x2 interactions, you get the total energy of the system that holds it together. This is the amount of energy that is needed to hold all of them together on the unit circle. If you have less, the unit circle will explode and they will drift apart. So this is what the quantity that is needed. And I put here H because this is known as the Hamiltonian in the literature. So you can ask a very simple question. So let's say you have your three particles on the unit circle, and you want to ask how much energy do you need to just add one more, okay? And so you definitely want to place it in the place where it takes the least energy to do so, right? So there exists such a point, and if this new particle is at location Z, then the amount of energy that you need to put it here is basically given by this sum of the interactions. Sum of the interactions of Z with Z1, Z2, Z3, right? So the place where it's easiest to place it is going to be the location where this energy is minimized. And you want to then ask the question, so how much of this energy do you need to add one more particle? And this is just a minimization problem. You just want to minimize the sum of these logs. And the point where the minimum is attained is where inserting it is going to be easiest. So this is definitely somehow the wrong question to ask. Oh, I don't understand. Okay, now this is really a bit out of whack. Okay, let's see. Okay, so this is definitely not how you should be solving this problem. If you have 4 of them, you can definitely find the minimum. If you have 10 to the 23, this is going to be quite difficult. And there might be many minimums. And in general, you won't get any kind of reasonable answer if you have 10 to the 23 of these particles spread around the unit circle. So this is not how physicists think about this. Usually they introduce some other external parameters in the system. So for example, they say that, okay, this whole thing is submerged in some kind of room that has a temperature. And they kind of impose the constraint that this whole thing is at equilibrium at this temperature. So, I mean, I don't know, this is gonna, I don't understand what is happening. Yeah, it just keeps jumping. Okay, so basically a physicist, he would introduce some other global parameter. Let's say he would impose the constraint that these charges are at certain temperature, outside temperature. And the point of doing this is that when you impose such a constraint, you actually narrow down the number of possible configurations. So the point is that, for example, if the temperature is very cold, then we know from physical experience things freeze. And when they freeze, they kind of start looking the same. And that's because there's not a lot of configuration. They kind of freeze in a, for example, grid. Okay? So the point is that when you impose this constraint of external temperature, you narrow down the number of configurations that can occur. But how do you narrow down this number? You narrow it down because you actually impose probabilities associated with each configuration. So for example, if it's close to absolute zero, then one configuration gets a very high probability, and all of the other one gets kind of a low probability, okay? And so if you impose this kind of external constraint, it starts to make sense. This problem becomes more well posed. You can actually ask, okay, what is the minimum energy that I need to insert a new particle? And maybe more correctly is not to think about adding, but to think about how much the energy, the total energy would change if you insert one more. That's maybe more correct. That's all right. Just to give you an idea of the effect of the temperature. So if we have infinite temperature, then this temperature basically destroys all the interactions between the particles. They become completely random, and you're essentially dealing with a random collection of points. So if the temperature is infinite, it is basically overwhelming any kind of force that there could be between them, and this just becomes random points on the unit circle. And this is how random points look on the unit circle. But now let's say we impose a temperature constraint, and look what happens, we get this. The points start to become spread out in a sort of regular way. This is the effect of temperature. And in this case, the temperature is actually very high. I'm not even being modest here. I'm not putting something like room temperature. This is extremely hot, and it already has this effect of imposing kind of regular spacing, right? And at room temperature, it will be even more kind of spread out. And if the temperature will be zero, then they will be perfectly distributed, like roots of unity. Okay? And so basically we have this, we now ask the reformulated question. So we have n of these particles on the unit circle. We now submerge this unit circle in some temperature. And we ask the question, what is the smallest amount of energy that I need to insert one more particle? And so by smallest amount, I just mean the amount for typical configurations. And usually what happens is that there is a very sharp transition in the answer. So some answer is extremely unlikely, then there's a sharp threshold, and everything above that is also extremely unlikely. So, or very likely. And then you know that that the answer is basically at this threshold. So in the same way, for example, if you take a material, it's either broken or it's together, but that's actually a question of probabilities that holds it together. There is a sharp threshold between being broken and being together. And it's just so sharp that we never perceive the transition. Okay, and so this is the question that we want to ask. And maybe I want to make one comment, which is kind of interesting. Maybe later. Okay, so maybe let me get a bit more precise about how we think about the probability of these configurations. So now maybe I want to make a side comment, which is a little bit illuminating why this physics perspective is interesting. So let's say that you have a polynomial, and you just have roots. You just have roots on the unit circle. You have roots on the unit circle, right? And you want to find out where is the maximum of this polynomial located. So the maximum will be located at the point where it's easiest to insert the new charge. So for example, you can think of a polynomial like z to the minus 1 to the power n. Then you have n of n particles here. So it's going to be extremely difficult to insert a particle here. That is very obvious. And also physically, it's obvious the easiest point is going to be as far away as possible here. And that's actually the maximum, 2 to the n, right? So then, similarly, if you think about something which is somewhat well distributed, but enters a gap, then also intuitively, the point where it's easiest to insert is where there is a gap. And that will be the maximum too. Okay, so it kind of like this physical intuition illuminates a little bit to some extent. Okay, so I want to go back to the effect of this temperature on the question. So basically the question is, how does we describe the most likely configuration? So we have a bunch of these particles. There is a temperature applied to them. And then we want to describe what are the likely configurations that can happen.
So when you say temperature, you mean you're just changing this log 1 over c1 minus c2 to a different function?
No. So basically this is the same. This is always the same. But this thing is surrounded by, let's say, 240 kelvins or whatever. And then if it's going to be in equilibrium, then these guys will have to lie in a certain configuration. So for example, if you have zero, absolute zero, then the only likely configuration is roots of unity.
Well,
Perfect
space.
space.
But I'm just wondering what mathematics goes into the temperature.
Okay, we'll get to this. We're getting to this right now. Okay, so I'll get to the details right now. Okay, so basically this is the details of how you describe the configuration. So we have, you see, we have this kind of system, it's at equilibrium. And now we have a probability density function associated with each configuration. So the probability density function is basically this exponential of minus beta of the total energy of the system. Okay, and then it's divided by a normalizing factor, which is the integral over all the possible configurations. And so this beta is 1 over kt. K is just a constant, the Boltzmann constant. And so this is the joint probability density function assigned to each configuration. And from this, you can compute the one which is the most likely. So let me give you an example of this. Let's say that temperature goes to 0. Then beta goes to infinity. Then this actually starts to go faster to 0, except at the h, which is the smallest. So from this, you kind of deduce that when the temperature goes to 0, the configuration, there's only one configuration that survives, and it's the one with the least energy. So this is a classical physics fact, right? You want to, and this function z beta n is called the partition function in physics. So this is kind of what I mentioned, and also you notice another thing. So when t goes to infinity, all of these configurations become equally likely, because the system becomes completely chaotic. And so how do you deduce this, this kind of probability density function? You basically deduce it from the fact that the entropy has to minimize at the it has to, the change of rate, it has to stabilize at equilibrium. So from that, you can compute this. Okay, so now let me get to more mathematical. Now let me get to mathematics. So this is just the physical interpretation of the problem. So let me get to mathematics. So to random matrices. So roughly the point is the following. If you take a n by n unitary random matrix, so what I mean by a random unitary matrix, I mean a matrix that you construct in the following way. You have some entries, and then you pick this row entries from the unit circle at random. Then you pick this row to be anything that is orthogonal to this, but also in the unit circle at random. Then you do the same orthogonal to this, but uniformly at random. And you build up a unitary matrix, which is random. All the entries are from the unit circle. And so what happens is that then you can ask, what is the probability density function of the eigenvalues of such a matrix? And the probability density function is actually given by this. So if the eigenvalues are a lambda1, lambda2 up to lambda n, then all these eigenvalues actually lie on the unit circle. And you can start thinking of them as your particles. And the probability of the eigenvalues lying in a certain configuration is exactly given by the partition function, just like the particles, but at a very specific temperature. This beta has to be 2.
So those are matrices with complex numbers. I thought the probability of any given matrix was 0.
Oh, this is the probability density function. So, okay, you want to look at the probability that the eigenvalues are, let's say, in an epsilon bow, right? So you integrate over this epsilon bow around this with this function. Yeah. So indeed, if you want specific, is 0.
But that's not specific.
This is the PDF, right? So you have to integrate in a neighborhood to get something. So the point is that there is a correspondence. You see, if we ask about particles at a given temperature, they have a certain probability of being in a given configuration. And that is actually the same as thinking of these as eigenvalues of a random unitary matrix at a given temperature. So, sorry?
Usually random matrices don't have temperature, or?
No, but why do you need why? Okay, but you see, okay, so this is unitary, right? And then you have some other betas. Beta 1 is orthogonal, beta equals 4 is symplectic matrices. And then you have a general ensemble, which is called the circularly beta ensemble. And that's just the ensemble of random matrices where the eigenvalues are sampled with this law. So, I mean, this is actually the kind of physical motivation for random matrix, the statistical mechanics motivation for the subject, which I find completely beautiful. I mean, I find it completely beautiful that these eigenvalues, you can think of them as particles with this type of interactions at a certain temperature. So,
just because the density function are the same, so you identify the.
Yeah, they're the same. So literally, this literally solves this problem. It is the same thing, right? I mean, if you think about these eigenvalues as particles, it is literally the probability is exactly like the probability of these particles being at a temperature. It's exactly the same thing. So now you see that you can deploy all the tools of random matrix to actually solve the physical problem. But what we can do, which is more interesting for us, we can reformulate the problem, the random matrix theory problem. And we're going to get a very natural problem. So for example, let's try to reinterpret this physically. So I'm going to take a random unitary matrix. So it has eigenvalues on the unit circle, let's say here. And then I'm interested in the determinant z minus un, right? So minus log of this determinant is the sum of these interactions. So the value of the determinant at this point, let's say z, is actually exactly the energy that you need to insert a particle at this location. So it gives you a physical interpretation of what it means, what the determinant means of a random matrix. And so then when you think about it, so what is the minimal energy that you need to insert a particle at location z for a given configuration? That's going to be the minimum of minus the log, and the minimum of minus is minus the max. So basically, we have the problem of finding the maximum of the determinant of a random matrix. This is an equivalent formulation of that physical problem. We're interested in the distribution law of this maximum of an n by n random matrix. And so we get to the random matrix problem from the physics problem. So we're basically, the physics problem that we started is the following. We had n particles on the unit circle, and they are kind of configured according to the fact that they are at a certain temperature. And we want to ask what is the minimal energy you need to insert a new particle. And this physics problem is exactly equivalent to asking about what is the maximum of the log of the determinant of a random matrix, random n by n unitary matrix. And so that's the question that I want to focus on. But so, okay, in fact, this question has an answer, which I can give you right now. So this is a question that was asked by Fyodorov, Hiary, Keating. And they have an answer to this question. So they take a n by n random unitary matrix, and then they conjecture that the probability that that this maximum is bigger than log n minus 3/4 log n plus delta converges for distribution function. And the distribution function is very, very concentrated. So we have that effect for all matrices. And the conjecture is extremely precise. They even relay the shape of the space transition. So they describe how it happens. And so this is a conjecture that was asked 10 years ago. And I think in number theory, we are used to easy conjectures in random matrices that kind of get solved within 6 months or 2 weeks. But this was a difficult conjecture in random matrices, which took 10 years and took the attention of a lot of people in the field. So there's been quite a lot of activity just on this question. And this question is also related to other things in physics related to Gaussian free field, which I cannot tell you much about. And finally, this question got basically solved last year by Eliot Paquette, who is at McGill, and Zeytouni from, I think, NYU and Israel. Yeah. So this is really beautiful work. I mean, I think it's a long paper, complicated, 100 plus pages. And they basically solve everything except, I think, the description, the exact description of the limit law, if that's correct. But even then, they still say a lot about it. Just a very, very little thing missing. Okay. And but here is the kind of catch. So given my introduction, you might think that the motivation for this conjecture was physics, and that's kind of partly true. But the main motivation for this conjecture was actually the Riemann zeta function. So, and this is a bit unusual. So, so let me explain why the zeta function can be a motivation for this conjecture. So let me maybe first define the Riemann zeta function. So the Riemann zeta function is defined as just this series, convergent for real part of S bigger than 1. And it's not a particularly interesting series until you analytically continue it. Okay, it is interesting, even if you don't analytically continue it. So the reason why it's interesting is because there is an Euler product. Yeah, yeah, sorry. This is interesting. Yeah. Okay, so it has an Euler product, and this was observed by Euler. Assume that there's finitely many primes, then this is finite. Let S tend to 1, this diverges, so there's actually infinitely many primes, right? And you can actually then boost this argument. You can deduce from it that, for example, this is divergent. And what Euler did, he wrote that this is log of infinity, because he actually wanted to say that he knew how quickly it diverges. It diverges like log. Okay, and so the next step. Okay, so I mean, so yeah, he did. He knew. He did write this. Yeah. No, really, he didn't. Yeah. Okay, so then if you're in the 19th century and you just discover complex analysis, you start wanting to analytically continue every function you can. And of course, this was not a exception. So one way that you can analytically continue this function, you can just write it as an integral, and then you can just integrate by parts. And this will give you an analytic continuation to the whole complex plane. So that's one way that this was actually accomplished. And so this is actually one of the major functions in number theory. Let me explain why. So one of the main appeals of the zeta function is that you can use complex analysis to capture two main features about the integers. So the first feature I already mentioned, there is an Euler product. And this is equivalent to the fact that all integers factor uniquely into primes. And then there's also another fact, which is the functional equation. So if you consider this type of zeta function multiplied by a gamma and pi, then you notice that there's actually a symmetry around the line S1 minus S. So around the line a half. And the relevance of this is a bit harder to understand. This is a bit less clear. The point is that this is equivalent to the integers forming a lattice. So in the zeta function, you have two features at once, multiplication and then also addition. And you capture them at once. And this is supposed to explain everything or most things about the integers. Just these two things. So why is this related to integers being on a lattice? The point is that from this, you can deduce Poisson summation formula. In fact, it's equivalent. So, and then Poisson summation formula is always true only because something is on a lattice or forms a lattice. So in this case, you see that the function equation is equivalent to the integers forming a lattice. So maybe I'll just mention how this deduction goes, because not quite obvious. So if you want to deduce the function equation, you basically take a specialized f, like maybe Gaussian, and then you integrate. And if you want to deduce this from the function equation, you multiply this by some kind of Mellin transform, and you integrate. So it's this type of deduction. Okay. And so, so what is one of the main fascinations of the zeta function? The kind of point is that the zeros appear to have a dual object, which are the primes have a dual object which appear to be the zeros of the zeta function. So if you want to see it very naively, this is maybe, you can just notice that there are two product representations. So one product representation is as an Euler product. The other one is just as a Hadamard product. So then you can just equate the two very naively, and then you can claim there is a connection, right? So this is the, okay, this is maybe not great, but this is one way of seeing that there should be a connection. And you can then do this argument carefully, more like a professional, and you will find, and you will find that, and you will find basically a really concrete relation between primes and zeros. And this is something known as the explicit formula. And the relationship says the following: if you want to count the number of primes up to x, this is actually equivalent to summing the zeros, but with this weight x to the rho. And now you have a very nice connection, right? Because now you see that if you know something about the zeros, for example, if all the zeros are on the line a half, then this is x to the half, and then you can count the primes. But this also goes the other way around. If you knew how to count the primes, you would also know the zeros. So if you knew that the primes are x plus x to the half, you would know that all the real parts are on the line a half. And so I think when people who are more algebraic see this formula, they conclude that the subject is over. Because we have primes, zeros, what else is there to know? It's here, right? There's nothing else. We have a formula. What else is there to ask? So, but unfortunately, it's not over because this formula is actually quite empty. That's the thing. It actually has very little content. And the reason why it doesn't have a lot of content is the following. So in this formula, the primes and the zeros are related a little bit in a Fourier type of way. So what I mean by this is that if you are interested, if let's say you are interested in knowing whether a specific integer is prime, let's say something at 10 to the 9, you just want to zoom at a specific integer just to detect if it's primes. Then what happens is that on the other side, you actually need to know a lot of zeros, right? And then that is not very helpful. And on the other hand, if let's say you just want to count the primes, but just count them, but not figure out individually where they are, then on the zeros, you actually don't need a lot of information. But there's also kind of, this seems like a kind of good situation, but there's also a drawback. If you want to know something very specific about the zeros, then you need to know a lot about the primes, right? So it's kind of, I mean, it's a type of Fourier uncertainty principle. Here, actually, you could have a function f, and here you would have a function f hat. And then the point is that you cannot localize both f and f hat. And this limits the use of this formula. And this is why the subject is not over. Okay, and so now you see that somehow the main actors are these zeros, and they're complex numbers. So you can ask two questions. You can ask about So vertical and horizontal behavior of the zeros. So let me tell you about the horizontal location. And I'm going to motivate why the Riemann hypothesis is true in 2 minutes. So, okay, so basically we can ask about the vertical location. So let's try to get an intuition on where they should lie. So one thing that happens from the function equation, if you look at this, if you look at the function equation, it's something like this: xc of s is xc1 minus s, and xc of s is pi minus s over 2, gamma s over 2, zeta s, right? So one thing that you could do, you could take this and you could try to balance it out. You could try to maybe take the square roots of these gamma factors so that the same ratio appears on both sides when s is a half plus it. And if you do this, you notice that there's a way of balancing this equation in a way that this ratio just becomes a complex number. So it becomes a complex number which is predictable, just e to the I theta t. So because of the function equation, there exists a phase which is just a normal function, just a completely regular function like t log t plus something something. And this function has the property that if you multiply zeta by this function, then it becomes real. In fact, it becomes a trigonometric polynomial with cosine predictable function minus t log n. So this is actually quite astonishing because it means that if you want to know the argument of the zeta function modulo 1, you actually know it right away. And this is something that happens only on the half-line. And it happens only on the half-line because you have this symmetry between s and 1 minus s. And so if you're a 19th century analyst, you actually conclude that 100% of the zeros should be on the half-line. And the reason for this, the kind of very naive reason for this, is very simple. You have a simple normalization, and it's a very simple reason. So let's say you have a function which is real, right? To ensure that there's a zero of a real function, you just need a sign change. So you just need to detect that it was positive and then it was negative. It doesn't require much. It's actually quite likely, right, that the function is positive then negative. On the other hand, if you want a zero of a complex function, then something magical needs to happen. The real part needs to be zero, but at the same time, this is not enough to just guarantee a sign change of the real part. You have to guarantee at exactly the same place that the imaginary part is zero. And that's much more unlikely to happen. So just on the basis of this, you expect that the majority of zeros will be on the half-line. So this is a little bit bogus what I said, because of course, the function could maybe diverge and then it's always positive and then there are no zeros, right? That could happen. But in this case, you have this representation as a trigonometric polynomial, and this trigonometric polynomial oscillates at exactly the same speed as the number of zeros. So you actually expect that it will account for 100% of them. And this is in fact a conjecture. So it's a conjecture that whenever you have a zeta function-like object that has a functional equation but maybe no Euler product, 100% of the zeros should be on the half. But then there could be exceptions. And then in the case of the zeta function, what is also conjectured is that these exceptions are ruled out by the Euler product. So it's resolved by the 0% of the half-line. That's right. Yeah, that's right. And in fact, there is quite a bit of evidence for this. I mean, there are some papers of Bombieri-Henschel, and they actually assume some reasonable things about the zeros, and they look at linear combinations. So then linear combinations have a functional equation but no Euler product, and they prove 100% of zeros.
Yeah, they're also numerical, even for L function attached to it, you happen to go.
Yeah, exactly. Same.
And
It's the same.
You know, but numerically there are also some off. Yeah.
Exactly, there's some off because
so,
you
cannot be cut by the prime because they don't have an order product.
Yeah, exactly. The ones that are off, you have to kill with the Euler product. Yeah, this is somehow the situation. So, okay, so this was the horizontal location. This is why we believe the Riemann hypothesis in some way. But let me tell you about the horizontal location. So, Dirichlet function.
Any functions.
Yeah.
You expect 100%.
Yeah, that's right. And this is kind of a theorem under very reasonable assumptions on like, yeah. So you take like, for example, LSK1 plus LSK2 plus LSK3, and all of these have the same modulus, primitive of same modulus, and then you make a very reasonable assumption about the zeros, really modest, just that the spacings are not too close too often, and then you show 100%. That was done by Bombieri and Hedgehog.
Get like a constant T over.
So you get basically T over square root log T. Or T, okay, you bet the number of exceptions is actually T log T over square root log T. So it's actually, yeah. 1 over square root log T is the density of exceptions. And they lie like within, it's interesting actually.
And why do you need the primes to put everything on the line?
Yeah.
And why do you need the primes?
Okay. You need the primes for the following reason. So basically, if you can think of zeta function as somehow like quasi-periodic function, right? So for example, you would think that if you have one exception, you should have T exceptions. And that's actually what happens here too. If you have one exception, let's say on the line 3/4, you have actually about T of them. But the Euler product allows you to take the log. And when you take the log, you can prove good zero density results, which are like T to the 1 minus delta. So then there should be 0. Because if there was 1, you actually expect T. But if you have T1 minus delta, it should be 0. I don't know if this is, I don't know if this is appealing as a reason. Okay, it's good.
If you think that prime are random, then it puts it puts all the zero at 1/2, no? Just because of
Yeah.
this explicit formula? Because then the error term should be to the 1/2 or.
Yeah, guys, I don't know. I mean, maybe I'll continue. And then, yeah, because okay. So I want to talk a bit about the horizontal location. So this was first done by Montgomery. So the average spacing is kind of 2 pi over log T between the zeros. Yeah, this is how the average spacing. And what Montgomery did, he actually normalized by the spacing and he summed over the differences between the zeros. So he looked how often the pairs are small. And his reason for this was to disprove SIGO zeros, so another story. But he did this for that reason. And he found that the limit exists, a rather unusual limit. And the point is that this limit is the same as the limit that you get if you look at the spacing of the eigenangles of random unitary matrices. So if you take, if you have a random unitary matrix with eigenvalue e to the 2 pi I tk, then if you look at the spacings, so you normalize by n because you have n of them, right? And then so you expect spacing to be 1 over n, roughly. So if you look at this normalized spacing, then it actually converges to the same limit. And so this was very surprising and gave some very weak evidence that perhaps you can model these zeros by basically n times the eigenangles. And so then this analogy actually persisted. So people computed higher correlations where these formulas get quite messy and cannot be accidental. And they match. They keep matching. And then there was also a computation made of all the spacings. And the numerical evidence was really great. So we kind of have this conjecture that if you take a typical T, if you just take a T at random, let's say on the half line, let's say this is the half line, and you take a T at random, and then you look at the zeros in a unit interval, then these zeros, or maybe gamma 1 minus T, is actually well modeled by the eigenangles of a typical random matrix. So the kind of correspondence is that you sample the T's at random, you look at the zeros minus T, and this is in correspondence with the eigenangles of some typical random matrix. So it's not a 1-by-1 correspondence. I cannot tell you, here's the random matrix, okay? But it's like a statistical correspondence, which works quite well for predicting gaps or other issues. Okay, and so it's actually kind of surprising how late this conjecture comes about, Because in fact, this conjecture could have been conjectured 100 years ago. Because 100 years ago, there was this Hilbert-Polya dream that maybe the Riemann hypothesis is true because the roots, the zeros, are eigenvalues of a large Hermitian matrix. And well, if it's a large Hermitian matrix, it's certainly very complicated. So it's basically kind of like a random matrix. So you see that it's fairly obvious, in fact, in retrospect. I mean, and already in the 60s, there was a lot of evidence that this is not just a dream, this is actually reality, because we have analogs of the zeta function. So you have the Selberg zeta function, and it's very analogous. It has a functional equation, has an Euler product, and its zeros are eigenvalues of the hyperbolic Laplacian. And a hyperbolic Laplacian is actually kind of like a large matrix. It's an operator, so you can model it by random matrix. And there was also another evidence in the case of finite fields, but I cannot tell you so much about it. So it's this work of Weil and Grothendieck. And I think the main issue was actually finding a good dictionary between the two. And even now, the dictionary is not great. Because when I was preparing this talk, I mean, I really struggled. I actually thought I don't understand what is the dictionary. So I had to look for maybe a few hours, and I did not find the dictionary. It just basically done a bit like, okay, this should be this, and it works, and that's all.
Dictionary, which forms?
Well, dictionary between zeros of zeta and eigenangles. Like people kind of improvise, you know, they say, okay, that was my impression, but at least I didn't find some kind of like consistent thing, you know, consistent recipe. If these are the zeros, then this is the eigenangles, then this is this. So,
Well, I think the problem there is that you've got analogies that work very well until they don't.
yeah, exactly. Yeah, exactly. Until yeah. So it's not, there's no like actual conjecture that tells you this is the recipe, you should do this, and then if somebody falsifies it, it's over. Okay, so now we can reformulate. You see, so we start with a problem in physics, we get a problem in random matrices, and now I can turn this problem into a Riemann zeta function problem, right? So this is the Riemann zeta function analog of the physics problem. We take the maximum, so there are typos here, there should be u. So we take basically t at random, and we ask what is the maximum in the unit interval around t. And so the t is random, and then maximum around that interval is the random variable depending on t. And we ask what is the distribution function. So specifically, what is the probability that this maximum is bigger than log t minus 3/4 log t plus some delta? And by analogy with random matrices, we conjecture that this should tend to some limiting distribution. The dictionary is that log of the n in random matrices becomes the log of t, because you have log t zeros in the unit interval. Okay, and so this is actually a result of mine. We show tightness, so we can actually get, we showed that at the scale of big O of 1, the conjecture is true. So we cannot get the limit distribution, but we can show that it's very tightly concentrated where it should be. And so there was also quite a lot of work before on this. So maybe let me explain why this is an interesting conjecture for the zeta function. This is maybe not as obvious as in the case of random matrices, where it was very natural from the beginning. So there are two reasons for this conjecture. So the original reason was that Fyodorov, Hiary, Keating were interested in the maximum of the zeta function. That's a kind of big and old conundrum in the topic. There are two candidates for the answer, and there's quite a bit of debate about which one is correct. And then there's a second reason which emerged a little bit later, maybe more subtle, and it has to do with this factor 3/4 that appears in the conjecture. And the point is that this factor 3/4 contradicted what most experts thought. Most experts expected this to be 1/4, not 3/4. And this factor 3/4 was actually some evidence that there's some branching phenomena that occurs in the Riemann zeta function. And then there was the question, what is this branching phenomenon? So how much time do I have? Do I have 15 minutes?
15 plus.
15 plus, okay. So let me explain the 1/4 factor. So kind of the expert thinking was basically that zeta has on average a half log t zeros. So you expect that basically if you shift the zeta function by 1 over log t, you might hit a 0. So as I like to say, the function could go from hero to 0. So anything could happen. So you would expect that actually these might behave like completely independent random variables because of this. So most experts thought and still think this way. It's actually a very useful way of thinking. And then there's a second way that we think about the zeta function. There's a theorem of Selberg that tells you that the proportion of values that hit between alpha and beta with this normalization is a Gaussian. So it's as if it was a central limit theorem for the zeta function. And the point is that when you put these two things together, it gives you a conjecture for the maximum. The point is that if this is really like just log t independent realizations, then the probability of this happening is basically 1 minus the probability that everything is less than v times n, where n is the number of independent copies. And then Selberg's theorem tells you that this should be like a Gaussian. And then you do this very simple math, and you find that the maximum should be log t minus 1/4. And this is a bit upsetting. So basically, if 1/4 is right, then random matrix theory is wrong, which is very big news. And if 3/4 is correct, our intuition is wrong, which is also big news. So this was interesting for that point of view. And it kind of suggested that maybe the maximum is not a half, like suggested by Selberg's theorem, but actually 1 minus little of 1. But this was discredited, so I won't talk much about this. So how to make sense of this exponent 3/4? It actually is related to something called branching random walks, branching Brownian motion. It appears first in the work of Bramson, he was interested in solving a PD of this type. And what happens that this PD, actually, you can write down explicit solution for this PD. Basically, the solution is 1 minus the probability that something called branching Brownian motion is bigger than x at time t. And what is branching Brownian motion? It's simply a random walk that is really a random walk. And then after time 1, it splits into 2 trajectories. And then at time 2, each trajectory splits again. And then they just continue splitting. And the solution to this PD was this maximum at time t. This was actually the solution. And the point is that you think, okay, you think we're done. But the problem is that finding this maximum is not good. You still want to analyze the solution and figure out where everything is. Just I got much more structure. Okay, and so this was actually done by Bramson. He actually analyzed this thing, and he showed that if you take x to be t minus 3/4 log t, then this converges to a limit. And you see, this is the same thing. T minus 3/4 log t. If I take t to be log t, I get my conjecture. Right? This is not an accident. So then you ask, okay, is there branching in the Riemann zeta function? And the answer is yes. So you can imagine that the zeta function is just like an Euler product, so a sum over primes. And then you can think of this sum over primes as basically a random walk. So the t is the random walk that you select, and then you make x go from 2 to t, and that's the evolution of your random walk that you selected at t. And then what happens, you notice one thing, is that if you pick 2 of these kind of random walks, which are nearby, then the previous heuristic would tell you that if they are 1 over log t apart, they should evolve completely independently. But that's not what happens. It's actually easy to see that this is not what happens. If you take t1 minus t2 like 1 over log x, these phases actually are about the same. So if you look at the evolution, it actually matches. These 2 like random walks actually match up to time e to the x. So in fact, the zeta function is more correctly modeled, the maximum is more correctly modeled like a branching random walk.
P up to x.
P up to x.
Not the exponential twice.
Yes. Yeah. Okay, and so this explains like the occurrence of this branching. And so I want to just finish very quickly. How do we prove the results for the zeta function? We actually really go back to the work of Bramson, and we strip it of all of the technology, because we cannot do a lot for the zeta function. We have to be as basic as possible. And the main kind of guiding observation in the work of Bramson is that you don't just determine the maximum, you actually prove how the maximal branch has to evolve. And you prove basically that the maximal branch has to tend to the maximum in basically a linear fashion. So here is, for example, a maximal branch. You see it's basically a linear function. This is how it looks. And then the proof shows that there's basically just one such branch, more or less on average. And so maybe just a few final words. So in the zeta function, as I said, we have to be very basic. We have very few tools that we can use. And I think also that the result that we prove tightness is probably quite a bit the last word on the subject for quite a while. Okay, so I think I will finish here. So, thank you.
Thank you very much for the beautiful talk. Questions?
Okay. I sense attention there with Dima also.
So this thing for the zero regions that you mentioned, does this strategy work to prove zero regions? Maybe not, well, obviously not the Riemann hypothesis, but something close to a zero region.
Okay.
Taking 1, 0 and replicating it and
you mean like putting the zeros rather than excluding them?
excluding zeros from a region.
Okay. So what is the strategy?
Well, what you said. You take 1, 0, you force it to replicate many times, right. But then zero displacements.
Yeah, that's like a dream in the subject. So this is really like a dream problem. Show that there exists 1, 0, there exists infinitely many. That would be a terrific result because then you could start actually trying to get this contradiction. So Bombieri tried this problem and failed completely. And I mean, I also tried this problem and I also failed completely. And I think the problem with the problem is that we have no idea how to do it because you just have 1, 0 and what can you do with it, right? You just have a 0 like at some location here. And the problem is that you go high up and high up, you don't even see that 0. So it's as if it didn't exist. So you have to stay very low, close to the 0, and what can you do there? You see, but that would be a fantastic result, that somehow there cannot be finitely many exceptions to the Riemann hypothesis. That would be a really beautiful result.
So in your branching random walk picture, just even at one random walk, it seems like you have a very good statement about how close to a random walk it is.
Oh, yeah.
So I wonder if you've thought to try to prove the Montgomery-Dyson conjecture with something like that.
You mean from, by Montgomery-Dyson, you mean the zeros, right?
Yeah.
So from the branching random walk thing.
Well, yeah, it's more like, yeah, exactly. It's in a different scaling, right? It's like one random walk and very nearby random walks, but you seem to be able to have.
Okay, so in other words, like, what does our work say about the zeros, right?
Yeah, do you have something to say? Yeah.
So I think basically nothing.
Okay.
So unfortunately, the reason is that this also, okay, this took a lot of time for me to also kind of understand. But so you have a representation for the zeta function. You can write it down. You can write down log of zeta as basically a sum over the primes up to x. And then you can write it down as a sum over the zeros in an interval which is 1 over log x. So there is a formula of this type. Here there is some oscillation. And the point is that you see if x is huge, this is tiny. And then it's just Euler product. If this is huge, this is tiny. It's just Hadamard product. But you can mix the two. And the conjecture is that these two terms are actually independent. That at this scale, they're completely independent. Anything that can happen here has no influence what can happen here. And the point is that our work only uses this guy. And basically does not use this guy at all. So whatever we say about this does not preclude anything happening with the zeros. So this one?
Oh, yours. Thank you.
Yeah. Oh, the same one.
This statement should suggest something about it.
It says
there is a
something.
short interval, generally roughly what we'd expect.
It says something, you know, kind of like maybe, I mean, Paul Bourgat, he thought more about this, but it says something very, very minor that somehow, I mean, it was so minor that I don't remember it basically.
But I mean, take the explicit formula, make x equals 1.
Okay.
I mean, okay, maybe you proved it over
Yes.
times, but you can now.
That's true.
substitute into here
Yeah, that's
the
true.
sum
That's
of the
true.
zeros.
Yeah, that's true. That's true. That's
Now,
true. Yeah.
You know, you could place your t, I don't know, on one side of the majority of zeros or something, and this is telling you something about the number of zeros close by.
Yeah, that's true.
But
Yeah, that's
you
true.
could-
Yeah, that's true.
you
That's
could
true.
probably say something about
Yeah,
it,
that's true.
but he's right.
Yeah, that's true. I actually agree. Yeah. I mean, it tells you something, but yeah, it's true. I mean, if you just think of it as zero, it tells you the maximum of this.
If you have a configuration of zeros, it's got 2 pi over log t, then you could compute the maximum. So just suppose you have 3 zeros in the
Yeah.
short interval, then you could find your t to maximize your heat or whatever, or energy. And so you could actually see what the maximum looks like in terms of zeros.
Yeah.
And the possible configuration.
Yeah, that's right. That's right.
And then compare that to what would be on the GUE.
Yeah, that's right. That's right. Yeah.
I mean,
Yeah,
there's
yeah.
a chance of actually saying something non-trivial. Really.
I mean, I think that's kind of what Paul says. He says that somehow this maximum arises from like very little deviations of zeros from, I don't know. I mean, we should talk to him. Yeah, Bulgar. Yeah.
It's sort of remarkable though that every way that you set up the zeros would be sort of tightly around log t.
Oh yes. Yeah.
That's crazy.
Okay, maybe I can tell you one more thing. So maybe what I can say is that no, maybe I won't say it. Yeah. I'm actually very reluctant to talk about what it means about the zeros, because I think it's actually very hard to understand this in a kind of very, to have an actual statement.
You seem to suggest that there's going to be a big gap, largest gap of zeros.
Yeah, that's somehow the naive intuition, but I'm also a bit, wary about it.
Will you somehow try to circumvent the zeros by approximating zeta by another product?
That's right. Yeah, everything is order product. So we basically don't touch the zeros when we prove this. Everything goes through the order product for as long as possible.
Suppose you've got 2 log of t here. What would that tell you about zeros?
At that point.
Yeah, suppose the maximum on short interval is 2 log of t.
So okay, so basically this is a question that you're looking at. So it's like one level density at Alessandro looks at this. So he looks at one level density at the points where it's high. And I think he actually notices a very, very tiny effect, like, a 1 over log t neighborhood, something repels a little bit, but it's very minor. This is why I'm kind of very reluctant to make some kind of big statement about the zeros.
So I guess if you use the explicit formula, the problem is about the error times like log t. What the issue is with trying to understand zeros? How to avoid log t error time?
I think it's just that we don't know their configuration at all. We know very little about how they could distribute.
I guess what I don't understand is you take your sum over zeros to a tiny pack, and then you've got plus big O or something.
Okay.
Now big O or something I think is log constant times log t. I'm not sure you can do much better than that. Maybe log t.
Okay, you mean you just want to approximate this by this?
Yeah.
Okay, so I'll give it to you.
Or your error term is too big to be useful in employing it here.
Somehow I don't think that's the issue.
No.
No. You can kind of assume it's this. There's not much harm.
I really don't understand why.
Okay. But we always get into this discussion. After every talk about zeta, you ask me what does it mean about the zeros. and Andrew, I have to say, I thought about this. This was my best answer, and I still did not manage. So you still managed to confuse me. And it's coming from a guy who wants to avoid the zeros.
I think there might be some interesting analog with your theorem for maybe like Laplacian embedded hyperbolic surfaces. Because there are now, for example, I think some nice results about correlations between these guys who are genus, right? So people And so, but I haven't seen anything about the maximum and
Yeah,
this kind of thing. So it because somehow, at least on the statistical side, people sort of predict what the relationship, like where this higher relation should be. But it would be nice to just formulate something about
the maximum.
Of what, and that should not be.
So you want to take like the sober zeta function? Yeah, okay, that should be. Yeah, that should have another.
But I think
and I think 99 is all actually.
yeah.
Thank you.